problems you want to look at? Do you want to go through the free response? What is it that we want to do today?
I'd say let's just get to the free response first.
Okay. All right. I think I've already done the spring 22. Like I said, you're looking at two things. Oh, no, maybe I haven't. Yeah, I've done these. Do you want to go through? Let's see if spring 21. I think spring 21 had a similar thing. Yeah. Okay. This is different. We haven't done these in class, so let's do these instead. These are spring 21 free response, and the ones that we're looking at that you will have would be number 1, although there's one part on here that's not on this one, and I'll do that, and then number 4. And that one looks like it's, yeah, that one's basically the same. So your free response will be very, very similar to these. I'll just change the numbers, but largely it's going to be the same. And then also, as I said in class, that I would also change, like, you know, where this is charge, that I could have charge, current, or voltage, that you need to be able to do these for all 3. So first of all, here for part A, actually, I'm not going to ask you this, how long does it take to completely charge the capacitor? But I might ask you that on the multiple choice. Actually, I probably will. So to do that, you first find the time constant. Remember, there are 2 times. There's the time constant, which is 5 times 2, which is equal to 10 seconds. And then there's the time to discharge or charge the capacitor, and that's equal to 10 times 10 seconds. So it's 10 times tau, which is going to be 100 seconds. All right, that won't be on your free response. I mean, you have to find the time constant just in the course of it, but it's not going to be on your free response. Part B, however, will be on the free response. That is, how long does it take for the capacitor to reach a certain charge of 10 microcoulombs? So in order to do that, we look at our equation sheet. I'm looking to charge this capacitor, and I want to know what is the charge on it. So I'm looking for this. It's a charging capacitor, and the charge is given by that equation. So I'm going to use that to find what is the time that it takes to get to a certain charge. So I say Q is equal to big Q times 1 minus e to the minus t over RC. Q is 10 microcoulombs. Big Q is C times V. That is the maximum charge that I have. So that's going to be 2 microfarads times 10 volts, or 20 microcoulombs, times 1 minus e to the minus t over RC. And then it's a matter of, actually, I know what R and C are, so I'll go and put that in. RC is equal to 10 seconds. So then I'm going to have to solve that for t. So I get 1/2 minus 1 is equal to negative e to the minus t over 10. Our negative 0.5 is equal to e to the minus t over 10. The negatives go away. And then I do the natural log of 0.5. The natural log of that is negative 0.69. Natural log of this side, natural log of this side, negative 0.69 is equal to minus t over 10. And then I solve that for t, and I get t equals 6.9 seconds. Okay, I want to see that you know how to solve that equation for t, dealing with that exponential function. Let's see, there was another part there too, right? I think I just asked, what is the charge at a particular time? I want to go back and look here. Oh no, I asked the percentage. So I also want to know what is the percentage. This is not asked on this, but I would ask at a certain time, let's say at t equal to, I don't know, 2 seconds, what is the percentage of the charge? Or what percentage is the charge of the maximum value? Is it at 50%, 70%? I want you to tell me what is the percentage. So I would say that what I'm really looking for is what is Q over Q. So that's going to equal to 1 minus e to the minus t over RC, which is 1 minus e to the minus, the time is 2 seconds, divided by the time constant, which is 10, and then whatever that is, you can do that in your calculator to find the percentage. Likewise, I want you to be able to draw the function that describes this. In this case, let's say I want to know what is the charge versus time. It would look like that. For a charging capacitor, it looks like that. Yeah.
So for the percentage problem, you would just you're plugging it in and then solving it. Okay, I got it.
Yeah. Yeah. Okay. I want to know what is the percentage, and then also be able to draw the graph. So I'll ask you three things. I'll ask you, what is the time when it's at a certain charge, voltage, or potential? I'll ask you, what is the percentage of the charge, voltage, or potential at a given time? And then I'll ask you to draw the charge, voltage, or potential over time. Joey?
How do you know what graph goes to which?
Okay, so if I look at my equation sheet, I see that the functions are either 1 minus e to the minus t over RC, or the functions are e to the minus t over RC. That's how you'll be able to tell them apart. This is a growth function. This is a decay function. So, I mean, there are physical reasons that you can think about, but probably for now, just the easiest thing is to say, this one is 1 minus, so it looks like this. This one is e to the minus t over RC, so it looks like that. Should look more like that. In fact, all three of these are going to look like this. They have that decay function built in. That e to the minus t over RC, that does a decay curve. Okay? That's probably the easiest way, just going from your equation sheet. All right. Now this one, number 4, is a similar question, and there are 2 parts to it. The first thing you have to do is to find the magnetic field at the point. So that's part A. I need the magnitude and the direction. To first just find the magnitude of that magnetic field, it's B equals mu naught I over 2 pi r. That's 4 pi times 10 to the minus 7. Here the current is 2 amps divided by 2 pi, and the radius is 0.25 meters, or that's the distance from the wire. Notice here I get some cancellations. That cancels. This leaves a 2 up here, so I get 16 times 10 to the minus 7 Tesla. So that is my magnetic field. Is that right? Yeah. 16 times 10 to the minus 7. So first find the magnitude of my magnetic field, and then I need to find the direction of my magnetic field. You let your thumb go in the direction of the current, like this. It goes into the page to the right of the wire and out of the page to the left of the wire. So my magnetic field would be into the page there, out of the page here. So it's going to be at the place of the electron is going to be in the plus z direction, or out of page. I would take either of those. Plus z or out of page. So that would be the first part. You'll have a question like that. It'll be different numbers, different configuration, different charge maybe. Notice here that the negative sign doesn't, the electron being negative doesn't matter, right? That doesn't affect the magnetic field that's produced by that wire. But it does affect the force. So the second part is I want to find the magnetic force. The magnitude of it is just QVB. So that's going to be Q, which is the charge of an electron, 1.6 times 10 to the minus 9. 9? It's 19, right? Yeah, sorry. V is the speed, 3 times 10 to the 5th meters per second. And then the magnetic field is 16 times 10 to the minus 7. So that gives me my force. It is whatever it is. Yeah, Octavia. You can calculate that. But then I also need to find the direction of that magnetic force. Now notice here this magnetic field is out of the page. So this electron is going through a magnetic field that's out of the page. So its velocity is to the right. I have to turn so my magnetic field is pointing away. So the force would be down. I would say that the force is down, except that this is an electron, so the force is actually up. So I'd give you you'd have to give me the magnitude, and then either tell me that it's either in the upward direction or the plus y direction. Either one of those would be correct.
And why is it going up whenever the E is going down?
Because it's an electron, so it has a negative charge.
So it's like repelling it, basically.
It just does the opposite of what you would think. So the right-hand rule describes the force that a positive particle would feel.
Oh.
So a negative particle will always do the opposite of what you would think. We saw that true with, moving low to high potential, right? That an electron moves low to high. It moves opposite the electric field lines. Likewise, it does the same here, that it feels a magnetic force that's opposite what you would expect. All right, so that's number 3 on your free response. The other free response that you'll have is a multi-loop circuit. I think we've done a lot of these. Let's see if there's one that we haven't done. Yeah, here's one that we haven't done. It'll look a lot like this. I'll have the currents labeled, but not their directions, just like this figure. Also, one of the branches you will find does not have a resistor. And so it will benefit you to pick the right loops. In this case, which loops would we pick to write the loop rule? I see that that bottom branch doesn't have a resistor. There's no resistor in this part of the circuit. So I would pick 2 loops. Which ones would I pick?
Big loop and bottom.
The big and the bottom. Right. So I'll take the big loop first and write the loop rule. I'll start here and go in this direction. Oh, I need to pick the directions for my currents. Doesn't matter what direction I pick. Just picking them like that for no reason whatsoever. So I'm going to have plus 2. I'm doing the big loop. Plus 4 plus 2I1 equals to 0. I think that's I1, isn't it? Yeah. All right, so plus 2, because I was going from little to big, plus 4, because I'm going from little to big, and then minus 2I1, because I'm going against the current. No, that should be plus 2I1, rather, because I'm going against the current. Then to do that's big, to do the bottom, let's start here, that's plus 2, minus 6I2, plus 8 equals to 0. All right, so I can solve each of these. I have 6I1 equals negative 3, and I2 is 5/3. Yeah, I think I'm doing this right. All right, so there's I1 and I2. I just solved, unfortunately, because I chose those loops correctly, there are equations with just a single unknown, so that makes it a lot easier. And then I use the junction rule. Pick any junction, doesn't matter. I have 2 currents going out and 1 current going in. I2 equals I1 plus I3. That's 5/3 equals negative 3 plus I3, and I solve that for I3. That's going to be 3 plus 5/3, 9/3 plus 5/3, 14/3 amps. So those are my answers. 14/3. It's positive, so this direction that I chose is correct. I2 is 5/3. It's positive, so this direction that I chose is correct. And then I1 was negative 3. It's negative, so this direction is actually wrong. It should be instead be to the left. Please, please, please write your equations very clearly, because that'll be one of the things that I'm looking for. If you miss the algebra, even if it's just a tiny algebra mistake, I probably won't even count half off. I'll probably say, oh, they just made a tiny little algebra mistake. But I have to see those equations. I want to see your 2 loop rules and your junction rule. That'll be really important. Make sure that it's clear and I can read it. And then be careful with getting the directions. Really, ideally, I want to see the right magnitudes and the right directions. That makes my life a lot easier if I just see that everything is right, because I can grade that much more quickly than if something's wrong. It takes me a while to go through and figure out exactly what's wrong. Okay? Y'all should be good at multi-loops, right? Like, I think y'all are pretty good at that. It's the other stuff. All right, what else do I want to look at? Those are the free response. Particular questions? Okay. 16 on 20. Yeah, so we did one of these like this in class. Two things. First, you need to know that the magnetic field runs from north to south. I think y'all know that. And then I want to figure out the direction of the force on one of those sides of the loop. I only need to pick one of the sides because I know the other side is going to go the opposite direction. Let's just pick, I don't know, this side right here. On this side, I have a wire that is coming out of the page. So that's my current. And the magnetic field is to the right. So the current is coming out of the page like this. And then the magnetic field is moving to the right. This is my current, this is my magnetic field. So then I want to determine what is the direction of the force. I is out of the page, the magnetic field is to the right. That means that my force has to be acting upward. So I have a force that's up. That means that this side is going to be up, and this side will have a downward force. So that's going to be, what's that? Counterclockwise, I think. Yeah, that'll be counterclockwise. Sometimes it's hard to see those three-dimensional vectors, but that's why this chapter is difficult, because you're thinking in 3 dimensions. But it's also why it's important. Okay.
I just didn't understand how you knew what was in and out of the page, but it's for the simplest, the way the arrows are.
Yeah, can you see on the how I'm doing my best to draw it 3-dimensional, but you know the magnet is in the plane of the page, and then this loop of wire is coming out of the page. Is that? Can you see it? I think I describe it as well. What happened? The loop has a, and then I just stopped. I don't know what happened here. If you have any questions, though, about the figures, I think that they're all clear. But if you have any questions about it during the exam, I'm going to ask. Well, I won't be there, but you can ask my wife. She'll be there. She'll know to answer your questions. Okay? And if she can't answer your questions, since I'm not there, just write the question in the margin of your test, and then send me an email afterwards. Then I'll go back and look at your question. And then if your question would have impacted what your answer was, then I'll make corrections for that.
Like this, if the arrows are coming down, like that would be out of the page.
Yeah, that's out of the page. So this is out of the page, and this is into the page. Going away from you. Into the page is away from you, out of the page is towards you. Okay? Yeah. When you get to light, so see right here, I see the word light. So that's where I'm going to stop. And unlike in previous exams, there's nothing about electricity anywhere past light. Light or radiation, if you see radiation. Oh, wait, no, here was one. Yeah, this is one, actually. I'm sorry about that. So let's take a look. Can I scan through them right quick? Let's make sure that's the case. So this is 22, the whole exam. It's exam 3. 23, excuse me, 21 stops at 13. 20 stops at 17. But then, oh gosh, I'm sorry. Yeah, there are some questions here, 27 and 28. And 29. Gosh, that was a long test. Oh, that was back during the pandemic. It was an online exam. I'll send y'all an email, okay, with outline, with all the questions, all right? I'll send that to you after this session. But nothing on light. Joey?
Can you do 17 on spring 20?
Mm-hmm.
I think I got it. I just want to.
Okay, so you will see one like this, something similar. And you'll see one like most of these, actually. But I have two wires, and I want to know what is the direction of the net magnetic field due to those two wires. One of the wires is out of the page. One of the wires is into the page. And I want to know what is the direction of the magnetic field here. So let's take this out of the page first. I know that there's a magnetic field that is in a circular path around this. If I use my right-hand rule, I find that it's counterclockwise. Not that right-hand rule, this one, like the Gigamaggies. So I let my thumb go in the direction of the current, and then my fingers wrap around to give the direction of the magnetic field. Anytime you're finding the direction of the magnetic field, well, no, that's not true. Anytime you're finding the direction of a magnetic field due to a long straight wire, that's when you use that right-hand rule. Thumb in the direction of the current, your fingers wrap around. So it's going to be a counterclockwise magnetic field. Now I could expand that circle, make it bigger up to point P. I find that a better way of doing that, neater anyway, because you write all these circles, they get messy. Draw a line that is radial away from the wire, and then my magnetic field vector is going to be perpendicular to that radial line. So my magnetic field vector will be in that direction, along the tangent to the circle. Similarly, over here, this is into the page, so my magnetic field is going to go in this direction, clockwise, and then if I draw a radial line, my magnetic field will be in that direction. So I have those two vectors. That means that my net vector is going to be in the direction of B. B is the right answer for this one. I think that's right. 17 is B. Yeah. Okay. Clear? What else? What other question do I have? Yeah. Isn't this spring 20? Okay. The wire here was not really necessary. You didn't really need to know the wire, that the wire was there. But again, though, this is a three-dimensional image. You'll see the three-dimensional image where the wire is coming out of the page. Can y'all see that? Is that clear to you? Is that clear? Not really. Anyway, the wire is coming out of the page. I just want to know, this wire is in between this north and south pole. I just want to know what is the direction of the magnetic field. But I know that magnetic fields run from north to south pole. So if it runs from north to south pole, then that means that the magnetic field is to the right. So it wasn't meant to be complicated. I just want you to know that the magnetic fields run from north to south pole.
How does the one run above it?
Yeah, so you will have to do this. In fact, this is in your free response where you have to find the magnetic field due to a long straight wire or straight wire. That magnetic field is equal to mu naught I over 2 pi r. So I want to know r here. R then is mu naught I over 2 pi b. So I just saw that 4 pi times 10 to the minus 7. I is 0.45 divided by 2 pi, and then b is 0.040. pi's cancel. That leaves it 2, 0.9 over 0.04. It's either mu naught. I'll show you on the equation sheet. I forget what the answer is. It's either A or C. Which is it? Do y'all know? I want to show you something else on that equation sheet too, though. So mu naught. There are several things that you need on the equation sheet. So you get the whole thing. This test, you need these things. Particularly, you need mu naught. You might need the mass of the electron or proton. You need the fundamental unit. That's if you have an electron or proton. That's the charge of those. You might also need to know the electric field, or rather, the force to an electric field is equal to Q times E. I worked through a problem like that yesterday, or the other day, where you have to know the force, the electric force, the force due to the electric field. You might need to know this expression for P, for household circuits, to calculate the load on a circuit. And then also you'll need to know, well, all of this stuff down through chapter 5. There's mu naught again, actually. Okay, so there's a lot on the equation sheet that you need. Just make sure you're familiar with it. I think we're almost done. All right, other questions? Yeah. Spring 22. Okay, yeah, so again, something, you're going to see all these, right? So you will see one like this too. This charge is in a magnetic field. The magnetic field is out of the page. Magnetic field is out of the page. So these show the magnetic field. The charge is moving in a circular path because it has this force that's acting on it. That force that's acting on it at this point is upward. Or I think I've done that before. Let's do it in the downward. Up here, the force is down. I know that it's down because if a particle is moving in this direction, then in order to follow a path that's like that, it has to have a force that's pulling down. Right? Like in circular motion, I have this force that is always towards the center of the circle, and that's true for your magnetic force. It will always be towards the center of the circle. It is a centripetal force. So that force is the centripetal force. The velocity vector is in this direction. So now the question I need to ask is, if this velocity was moving through this magnetic field, this is my magnetic field, is that the force that I would expect? I just imagine the force isn't there, I don't know it. My velocity is in that direction. My magnetic field is out of the page. So there should be a force that's upward acting on this particle. But there's not. It's a downward force. And because it's a downward force, that means that the particle is negative. It's opposite. So the force is opposite what I think it should be. So that means that the sign of the charge is negative. That's how mass effects work. Righty? What else? Oh, really sad. Is it sad, Dave? 17. Yeah, 17. Again, you're going to see something like this. 17, you have to know two things you have to do. First, you have to figure out the magnetic field at point A. I say F up here, but it's really A. So first, what is the magnetic field at point A? Do like we did previously. I have these magnetic fields that are being produced by these wires. So here it's into the page. So the magnetic field is clockwise. Then imagine if I draw a radial line at this point, that magnetic field is in that direction. Now due to these other wires, due to, say, this wire, the magnetic field is in that direction. And due to this wire, the magnetic field is in that direction. In each case, you can draw a radial line think about, is it clockwise or counterclockwise? In these cases, they're all clockwise. And then draw the vector that represents that force or that magnetic field. So the net magnetic field is going to be in this direction, because these two that are off on the side, they cancel out their x components, so they only have y components. So what I get is a magnetic field that's up and a current that is into the page. And then that's what we've done before. Current is into the page, magnetic field is up. That means that my force is to the right. That's a tough problem too, because you have to, both applications of your right-hand rule, and you have to do it multiple times. So a lot of right-hand rule stuff on this. If you're not getting the right-hand rule right now, then really need to work on that over the next 24 hours. That you get it between now and, well, 23 hours and 35 minutes. So is that bad to have a countdown? We should have a pop. Tick tock, tick tock. Oh, that would be mean. All right. What else, y'all? Answer all your questions for now? All right. I'm going out of town. We're going to Natchitoches this afternoon, but I'll respond to email. If you have burning questions, Dr. Verma, Dr. Young, they can answer your questions. Or you can email me. We can even chat if we need to on the telephone or over Zoom or whatever. I'll take my laptop with me so I'll have access to it. And again, if y'all have questions during the exam that you feel like you just have to know the answer and Dr. Young can't answer it, Dr. K. Young, my wife, then just write them in the margin of your test and then send me an email after the test. But ask her first. She should be able to answer your questions.